basically H2O, which is water, and HCl, which is hydrogen chloride. Note that the properties of the constituent elements, let's say for hydrogen, for water, the property of water, H2O, is very different from the property of hydrogen separately or oxygen separately. Just like HCl, this is an acid, it's corrosive. The property of this acid is very, very different from the property of the hydrogen differently, or the chlorine differently. Now, a mixture contains two or more constituents which can easily be separated by physical methods. In subsequent classes, we are going to be looking at separation techniques. We are going to find out that we actually use separation techniques to separate mixtures. Examples of mixtures are air, soil, urine, palm wine, Coca-Cola, milk, blood, crude oil, brass, seawater, etc. Separation techniques. Separation techniques are those methods that we use in separating the constituents of mixtures. The individual constituents of mixtures behave differently. They have different properties. They retain their respective properties. So if you have a mixture like crude oil, in Nigeria we have lots of deposits of crude oil. The constituent part of the, so that we can have the PMS, we can have the diesel, we can have the fuel that the aeroplane use. So how do you separate this mixture of crude oil in order for you to get the fuel, that the petrol that we use for cars, the one that airplane use, and the diesel for diesel engine? We use what we call separation technique. And the separation technique used here is fractional distillation, considering the boiling point, because the boiling point of PMS is different from that of diesel and is different from that of the AGO. So due to this difference in boiling point, which is a physical property, we can easily separate. Now you buy your rice from the market. You have stone inside the rice. Some of our locally made rice, you have stone and you have your rice. You can easily use sieving because of the difference in size of the stone and the rice. Also, difference in size between the seeds of the beans and the stone. So there has to be physical property that can easily differentiate one constituent of a mixture from the other for you to be able to separate them into two. We have different separation techniques. Separation techniques are actually used for specific kind of mixtures. So what are these kind of mixtures that need these various separation techniques? The separation techniques that we have are sieving, filtration, decantation, crystallization, fractional decrystallization, distillation, fractional distillation, magnetic separation, chromatography, and the rest of them. Now we are going to be looking at particular mixture and the suitable separation technique used. Sieving. When you have solids of different sizes, like in the sand of different sizes, you have to sieve. If you want to collect a specific sand side of a specific from the other one, you have to sieve it out to get the size that you need. If you have your rice and it's contaminated with stone, and the stone and the rice have different size, and you want to sieve out, you want to separate, you use sieving. Magnetic separation is used whenever you have magnetic solids and you want to separate them from non-magnetic ones, as in steel. So whenever you have metals that are magnetic and you want to separate them from non-magnetic ones, you use magnetic separation. We have decantation, filtration, and centrifugation. And these techniques can be used to separate insoluble solid from a liquid. So whenever you have insoluble solid, a solid that cannot dissolve in a liquid, you can separate it from the liquid using either of decantation, filtration, or centrifugation. You also have evaporation, crystallization, precipitation, and fractional distillation. And these techniques are used to separate soluble solid from a solution. When you have a soluble solid, that means solid that can actually dissolve in a solvent. If you want to separate them, then you use these, either evaporation, crystallization, precipitation, or fractional crystallization. Now you have another technique known as distillation, which is used to separate solvent from its solution. You also have fractional distillation, which is used to separate miscible liquids, just like we have in crude oil. We also have separating funnel, used to separate immiscible liquids. And we have chromatography, that is used to separate solids from a solution. So how does this come out in WAEC or JAMB or NACO? You're going to be asked which of the following methods can be used to separate solids of different sizes. And you have options: sieving, magnetic separation, decantation, and filtration. You are supposed to pick sieving. They're also going to ask you which of the following separation techniques can be used to separate solvent from its solution. You should know that it is distillation. Now, if you have substances that are impure, to get them to be pure, you used to use separation techniques to separate them, to separate the impurities from the main substance. So how do you test for purity? How do you know that a substance is pure? What can you use in checking to know that this substance is pure, that the proper separation has been done? Test for purity, of testing for purity, either by using the melting point or boiling point, or by using the chromatographic characteristics of the substance. Now, impurities make substances not to boil or melt at the specific temperature that they should, as it's written in the book. Actually, impurities decreases the melting point and also increases the boiling point for liquids. Impurities decreases the melting point for solid and increases the boiling point for liquids. So, for you to know whether a solid is pure, when it melts below the temperature that it should have melted, then you know it is impure. Whereas that of a liquid, it will now boil at a temperature that is higher than the normal boiling point. Also, in a chromogram, a pure substance produces a single spot, unlike an impure substance. So that is how you test for purity. So to make impure substances to be pure, they need to undergo purification using any of these separation techniques. Matter is made up of discrete or small particles, which can either be atoms, molecules, or ions. So matter, like me, you, the drugs we take, the food, anything around us that has mass and weight, is actually made up of discrete or small particles. And these particles, we can have what we call atoms, we can have molecules, we can have ions. Atoms, or an atom, is the smallest part or particle of an element. that can take part in a chemical reaction. You can have an atom of elements like phosphorus, an atom of sodium, an atom of calcium. Now, a molecule is the smallest particle of a substance that can actually exist alone and still retain the properties of that substance. You can have a molecule of hydrogen. An atom of hydrogen is written as H, whereas a molecule of hydrogen is written as H2. H subscript 2. Now, what is an ion? An ion is an atom or group of atoms that possess an electrical charge. Now we're going to look at these concepts one by one. So we are looking at the particulate nature of matter. How matter is actually made up of small particles. These discrete small particles can either be atom, molecule, or ion. Now, an atom is the smallest particle of an element which can take part in a chemical reaction. You can see this is phosphorus atom P, this is sulfur atom S. But now, if you have phosphorus that can stay alone, this might not be alone, it will be in the presence of other atoms. But now you have this P4. This is 4 atoms. It has an atomicity of 4. 4 atoms of phosphorus that are together, they can exist alone. We call it molecule. So a molecule is the smallest particle of a substance that can normally exist alone. Very, very important. Atom might not be able to stay alone, but molecules are able to exist alone and still retain the chemical properties of that very substance, be it element or with neon. Neon can stay alone with the atomicity of 1, just having 1 atom. Nitrogen, phosphorus, sulfur, the sulfur molecule, oxygen molecule, and ozone molecule. So all these are molecules. They can have more than 1 atom, but the atoms just have only 1 atom. Very, very importantly. Now we look at ions. An ion is an atom or group of atoms which possess an electric charge. If this charge is positive, then we'll call them cation, or we'll call it cation. But if it is negative, we'll call it what? Anion. So these 3 are the basics. Click down the notes, get down the notes so that you can easily understand in future when you go through it. Now, these 3 are the major discrete forms that matter can exist in. Very, very important. Atomicity is simply the number of atoms in one molecule. Like here now, the atomicity here is 4. Atomicity here is 8 because there are 8 atoms in one molecule. All these are molecules. But atom, the difference is that atom is just 1 single atom. But for molecule, it could be more than 1 atom. And these molecules can exist alone. You can see them in nature alone. Unlike what we... Whereas ions are actually charged. They are charged. So you can have something like this, Ca+. So you can have something like Na+. This is single positive charge, double positive charge. So all these are ions. Because they are positive, they are called cations. So example of anion is chlorine with negative charge. Non-metals are mostly anions. Non-metals are mostly anions. Non-metals are mostly negatively charged, whereas metals are mostly positively charged. So these are the three discrete particles that matter is made up of. Subsequent classes, we are going to be going into details of how to use these and understand them much better. John Dalton in 1808 helped us understand more about atoms, and he put forward the Dalton's atomic theory. This Dalton atomic theory over the years have undergone several changes and modifications because some of the statements through experiments have been proven to be wrong or cannot hold completely. So now we're going to look at the statements of the Dalton atomic theory, and at the same time I'll be mentioning or pointing out the modification or the modifications that have been done on these statements. So let's look at the first statement of Dalton's atomic theory. All elements are made up of small, indivisible particles called atoms. Is this true? Yes, because made up of atoms, small atoms. That these atoms are indivisible. Now, through the experiments of people like Rutherford, we're able to know that atoms are actually divisible. Atoms are actually made up of protons, neutrons, and electrons. So whereas the first part is true, the second part is not true. So this used to be very correct, but because of several experiments that have gone through in recent times, we are able to find out that atoms are actually divisible. Number two, atoms can neither be created nor destroyed. This still holds true for ordinary chemical reactions. But we know that in nuclear reactions, things like uranium can still be broken down into other atoms of other elements. This one, nuclear reactions, makes this very statement to be not completely true. Discovery of electrons, protons, and neutrons made this not to be completely correct. So these are the modifications to this, whereas nuclear reactions should be taken into consideration for you to have this to be true. Now, thirdly, we have that atoms of the same element are alike in every aspect and differ from atoms of all other elements. This is not completely true because of the discovery of isotopes. Now, in isotopes, we find out that one element, say chlorine, can have different isotopes. They can have the same chemical property, but the mass number will not be the same. So this is the modification to this. Now, when atoms combine with other atoms, they do so in simple ratio. This is actually correct for inorganic reactions. The combination between the combining atoms, different atoms, for inorganic reaction can occur in simple ratios. But when you have complex organic reactions, like that involving proteins or other things in organic chemistry, there is no simple ratio combination. You can have them in multiple ratios. Now we have the fifth statement of the Dalton atomic theory. All chemical changes result from the combination of this still holds true. So these are Dalton's atomic theory, and these are their modifications. So these modifications were born out of experiments that have been conducted since after Dalton in 1808. Since after John Dalton in 1808 put forward the following statements. Much of this statement has already been supported by things like the law of multiple proportion, the law of conservation of mass, and other laws. So in subsequent classes, we are going to be using those laws to do a lot of inferences. Thank you. Let's look at symbols of elements. Now, if you want to represent an element, or if you want to write it in an abbreviated form, and you want people to understand, you use what we call symbols of elements. Symbols of elements are simply the first letters. If the first letter is already taken, you can have the first letter plus the second letter as the symbol of an element. Now you can also have the first letter of the Latin version of that element, or the Latin name of the element, or the first letter of the Latin element and the second letter. So that is how we come about symbols of elements. So we're going to be looking at the first 20 elements and their symbols. Now let's look at element number 1, hydrogen. The first letter is H, so the symbol we are using H. Element number 2 is helium. Because H is already taken and it's also the first letter, now we use the first letter plus the second letter. So we have He as the symbol of helium. Lithium, we have Li. Beryllium, we have Be, because we already have boron as B. Carbon is C. Nitrogen is N. Oxygen is O. Fluorine is F. Neon is N. Sodium is N. Why is sodium N? Because the Latin name for sodium is natrium. So we are using this first two, Na. Sodium is Na. Sodium is Na because the Latin name is natrium. So we are using it as a symbol. Magnesium is Mg. Aluminium is Al. Silicon is Si. So the symbol can either be the first letter or the first letter plus the second letter. Hello, welcome. Let's continue with the first 20 elements and how we can memorize them and be able to use them. So we have the atomic numbers, which is increasing downwards, and we have the elements. We have hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, with atomic number 14. Then we have phosphorus, sulfur, chlorine,